The last time we discussed symmetry elements, which are planes or points or axes, and on which you perform a symmetry operation to move an object about it. For example, we did the mirror planes, which are sigmas, and we did axes of rotations, which are c's. And so a mirror plane is a plane, so the plane would be your symmetry element, and the reflection you perform through that symmetry element is the symmetry operation. And we decided that if we are moving an object through a symmetry element and it ends up in a position that's indistinguishable from the original position, then that's a valid symmetry operation or symmetry element. So the ones we have left are the inversion centers and the improper rotations. The improper rotations are actually a combination of two. They're kind of complicated, but I'll guide you through it. And then there's the easiest one, which is called an identity. Every object has an identity, even if it completely lacks all symmetry. An inversion center is simply a point through which you perform your symmetry operation. So these three molecules that I've shown here are fairly easy to spot and recognize that there is an inversion center. So it would be in the middle of each of these molecules, and then you perform your symmetry operation through that point at a straight line and that same distance. So what that means is if you have an inversion center and a molecule or an atom or a shape, let's say here we have an X and here we have, you know, an O, and so if you send those to shapes or elements or whatever you want to call them through that point, they would reflect here. This one would go through at a straight line, and so on a two-dimensional surface that's fairly easy to grasp. It becomes a little bit more involved when we're looking at three-dimensional shapes. So as always, I recommend you build and visualize, but the three I've chosen here should be pretty simple to see. If this is flat in the plane of the board, that each of these chlorines would simply exchange through that mirror plane through the inversion center, and so and then also the platinum just basically stays put. It's on the inversion center. So here, as long as the hydrogen peroxide is in the plane of the board and this is not rotated by any angle, we do have an inversion center. The minute you rotate that just by 5 degrees, you no longer have an inversion center, and that's something you may want to play with and look at, right? So but here that hydrogen would go straight through the center and then project into another hydrogen. And the same is true for the bonds and so on, right? And so here we have an octahedral, so we have 90-degree angles, and so it's like an X, Y, Z coordinate system. It's pretty easy to see that all the ammonia ligands would exchange, and so the minute you replace one of these ligands with a different ligand, you no longer have an inversion center. So we'll be looking at all these things in great detail. So next we're going to look at these 8 molecules and decide whether there is an inversion center or not. I suggest that you pause, go through this, and then once you've figured it out, or you think you've figured it out, resume the lecture and I will go through it briefly with you. Okay. So ammonia is pyramidal, and so if we are considering an inversion center, it would be on the nitrogen, which is fine for the nitrogen, but all of the hydrogens would project into space. And not only that, they would go from down, right, because these are all going down. It would go through the nitrogen and then come up. And all you need is one violation to rule it out. So this one does not have an inversion center. The last one, let's skip to the last one because it's also pretty easy to see. It's trigonal planar, and so you would project a fluorine into space here, and so we do not have an inversion center here. Diborane does have an inversion center, and so the square here, the boron hydrogen boron square, is easy to see. It's a little trickier to see that these project into each other, but they do. If I was to draw this on the side, like to rotate that, where the boron hydrogen boron basically is now in the plane here. So I'm going to draw it like this. The hydrogens are here, and so at least the terminal hydrogens, then it's easier to see that they would, because they are in a plane, that they would project into each other. So this, yes, we do have an inversion center for this one. Going on to the next one, we have benzene. We know benzene is flat. Again, you must recognize that these are delocalized. If they were not, we wouldn't have an inversion center, but as long as they're as drawn, all the carbons project into each other through that center, and so do the bonds. Of course, if I had cyclohexatriene, then you know, you would end up with bonds on opposite sides, right? So this would project into here, and so on. So that's no good. Cyclopentadiene is also flat, and so if there is an inversion center and you perform just one of these carbons through that inversion center, it would end up in space. So this one does not have an inversion center. Benzene does. Methane here, or any tetrahedral, does not have an inversion center. Should also be pretty easy to see that this would project into space. Let me show you real quick. It might be easier to see if we look at it this way. So I'm going to point one of these hydrogens, and by the way, you should always also look at, like, we have axes of rotations here, right? So we're going to look down the threefold axes, and so this hydrogen that points towards you guys would then point into space where I am, right? So this would go through the center and point up. So a tetrahedron does not have an inversion center. Moving on to ethane, staggered and eclipsed, it becomes a little bit harder to see. Now the eclipsed one does not, and so on paper it is kind of hard to see, although I don't know. I have a hard time seeing this, you know, like this. Oh, it looks like on paper this could project into it, but it doesn't, because this goes in the back, and then this would stay in the plane and would project right here. So we can rule that out. And whereas the staggered has an inversion center, so these all reflect into each other. But how easy is that to see for you? I don't know. So you may wanna build this. So the eclipsed one, once you build it, is pretty simple to see that this hydrogen would reflect through the center and end up between these two hydrogens here, right? So right now, the hydrogen that I am sending through the inversion center is pointed up and towards me, and then when I put it through the inversion center, it would end up again right here. So there's no inversion center. And then if you rotate that, of course, by 60 degrees, you end up with the staggered one, and so the staggered one, you do end up sending this through and in itself, and this happens for all of them. So the eclipsed does not have an inversion center, but the staggered one has an inversion center. So next we're going to do the identity, which is a 360-degree rotation. So that would be the operation, and so every molecule has one, even if it lacks symmetry altogether. And it's just a mathematical necessity, as we will see when we do Raman and IR bands. Looking forward to that, by the way. It's going to be fun. But for now, just understand it is a 360-degree rotation to get its own notation here in E. And so the hardest one is the improper rotation. So let me just first off say that this molecule shown does not have an S2, because an S2 is actually an inversion center. I'm just using that to explain what it is. So if we have, for example, an S2, that would translate into where we replace N with that 2, right? So it would be a C2 followed by a sigma H along that C2. So the way I've drawn this here, I have assigned the C2 through the nitrogen-nitrogen bond. So that's where I put the C2, so that you can follow that. So there isn't a C2 there. So that's also important to note. So if we had something like an S3 or an S4, that doesn't mean that that symmetry element is standalone. It's just once you've performed both of those operations, the combination, if it ends up being itself again, then we have an improper rotation. But so if you look at that C2 I drew through the nitrogen-nitrogen bond, and then you follow, let's follow that hydrogen here, it would point down now, okay? And so that's true for all four. Make sure that happens for all four. And then your sigma would be horizontal with respect to the C2, and so then this would project and end up here, right? Which is now the same as H4. So that would be an S2. Any inversion center is the same thing as an S2. So if you have an inversion center, you have an S2. But as I said, that's actually not an operation that we consider. We just call that an inversion center. So let's take a look at a couple more here, right? Eclipsed ethane has an S3, and it's a little easier to see. I'm not going to have to color code the hydrogens here. And that's probably because an S3, first of all, would be a C3 followed by a sigma H. And if we assign a C3 through the carbon-carbon bond, which there is a standalone C3, so we already have a C3 here, and we also have a horizontal mirror, a sigma H. So these two symmetry elements exist on their own, so you can just perform a C3 and then a sigma H, and in fact you can do any of the symmetry operations and combine them and end up with the same molecule. So, but it still is useful to go through something like that to illustrate that particular operation. If we have that, right, so we have a C3 already, and so if we do a C3 and then we perform a mirror, and you can go to that 3D Chem program too. Let's do that real quick. So I did a search on the ChemTube 3D, I put improper in there. I have a link for that, but you can do that yourself. And so here they're giving you all of these different eclipsed ferrocene, ethane, eclipsed, and whatnot. So let's click on that, and it shows you, if you click on the S3 rotation, it actually goes through with you. It shows you, see, the rotation, it shows you the axes, and then it does the reflection. There's the mirror, and then it rotates it beautifully so you can see where the mirror is. So that's done very nicely. But as I said, that one is pretty simple to figure out yourself. It's a little harder. It's little harder to see, for example, if you have methane, which has an S4. So it's a little harder to see because there's no C4 and there's no horizontal mirror plane. So that's a little harder to see. But what happens is if you perform a C2 here, well, we know we have a C2 here, right? That's fine. But if instead you do a C4 and then a horizontal mirror, that actually exists. So a perfect tetrahedron has an S4, but it doesn't have a C4, and it doesn't have a horizontal. It has mirrors, but it doesn't have a horizontal mirror, which is with respect to any of these principal or other axes that are there. So here I've color coded the operation of the S4 for methane again here, and so we are doing a C2 here, where let's just focus on H2. If we rotate that, it ends up here at a 90-degree angle, so obviously that's not a valid operation. But when you do the horizontal mirror through that, it ends up being in its original position, so we have an S4. One last example, and then I think we all had enough. So we are looking now at staggered ethane, and staggered ethane has an S6. This is an example of where we don't have independent C6s, and we do not have a sigma H. We do have an inversion center here. We have a C3. We have mirror planes, but none of them are horizontal, and they're all vertical mirror planes. And then we also, so that's the S6 would be a C6 followed by a mirror that goes through that C6. So here if we and if you look at this molecule down the carbon-carbon axes, you can tell that this is exactly, that's that 60-degree rotation that we are performing from the eclipsed to get to the staggered, which is just slightly lower in energy. So it does do the little twisting here, and that is a 60-degree angle, and that if we perform a C6, that 60-degree rotation, and then reflect horizontally, that it reflects into itself, where the hydrogens all go into themselves. So that is definitely a fun project for you to figure out. So the improper rotations are the most challenging. The good news is that we most likely won't have to decide, and but we can have some fun with symmetry now, right? So now you know all of the mirror planes, improper rotations, axes of rotations. You can run around the world and look at objects, you know, grab a friend. It's a really wonderful geeky moment, and start looking at stuff, you know. All right, I'm drinking coffee. I wonder if this has any symmetry. I don't know. Does it have a mirror plane, or, you know, or a salt shaker? This is really kind of fun. And different ones. Are there axes of rotations here? What about the holes? Are they going to destroy some of the symmetry? Is there symmetry there? So what about a soccer ball? You know, is that a C5 here? And so I tell you, when I learned this as an undergrad, I had a lot of fun. I was one of those super geeks, you know. So, and then you can start modifying here, right? So if you look at that Death Star, it doesn't really have any symmetry. It's got all of these imperfections here, and then you can kind of say, well, what if this was all smooth, right? And would we have a mirror plane? Would we have, you know, what if this was gone? What if this, you know? So just kind of play around with it. It can be fun. I'm not giving you this as homework, but so finally, play around with models and molecules. If you don't have them, go to these sites, and when we get back, we are actually going to use a flow chart. So go ahead and download that from the website, and or Google it. We're going to use a flow chart to assign a point group, and I'll elaborate more on what that is and why we use it later. Have a good one.